I guess we can start.
Okay.
Introduce
Yeah,
yourself.
thanks. I also want to thank Bastien for actually scheduling this for me. I think he did it especially for me. I don't think you were going to have a Wednesday talk this week because of spring break. But I was asked to give a presentation on this material at Lehigh University on Friday, so I'm going out there on Friday, and I thought it would be nice to do a dry run with you guys first. And, the other thing about this is you probably, those of you who know me, would assume automatically I'll be talking about roofs wherever I go, which is my day job. I mean, not just roofs, but urban environment. I work with Central Gross, so I guess you know, and I'm mostly immersed in urban island, urban runoff, urban infrastructure, energy, all those hard structure issues. But I do have I have a long background in paleoclimate, which I sort of moonlight on, I guess is the best word, and I do try to publish when on this particular topic I'm discussing today, when I feel I have something new to add or something's been developing in the field that I think it's important to address. I started on this work. I do want to say I started this line of inquiry that I'm going to try to summarize for you many years ago. I actually got started on this particular research question probably even before my postdoc with Barry Saltzman at Yale, who was doing Ice Age theory. He's now deceased, but it even goes back to when I was at NYU, Michael Gill and Ice Age research. So it's a very long-standing interest of mine. So that's why I'm talking about this. It's not a out of the blue topic. And the title of my talk is here, of course. And this is very interdisciplinary work, which is what excites me about it. It's certainly as interdisciplinary as I've ever gone, probably will ever do. Where I've been through the years trying to compare two very fundamental paleoclimate problems against each other that are not normally linked. And one of them relates to this picture, which is, and again, these two problems actually span major warming and cooling episodes of the Earth history. So one of the problems exists during the super greenhouse era of the Cretaceous. We'll use that as the example time frame. And the other problem, which I'll get to, is the ice house era, the 100 to kill you cycle. So these are very major cycles that we're talking about here. And the Cretaceous problem that I'm going to be dealing with is sort of summarized a little bit with this picture. This is a perspectives piece from Ken Miller in Nature Geoscience not too long ago, where they titled Broken Greenhouse Windows, where they were proposing the existence of Cretaceous ice sheets on Antarctica. This actually is a model run from DeCanto and Pollard, where they were experimenting with the idea that could you generate ice sheets at this time, which is believed to be a high CO2 world for sure. I think in this model they were actually able to get some ice volume developing on Antarctica when they brought the CO2 levels below 650 ppm or so. These are no small ice sheets if they existed during the Cretaceous. They're about 25-meter equivalent, which is what they're aiming for with this work, to try to explain some sea level data, which I'll refer to a little bit. But 25 meters is not a small Antarctic ice sheet. In fact, the numbers have been coming down from the old days when we used to quote Antarctic ice volume. When I was in postgraduate phases, 70 meters. But I'm finding that the new numbers seem to be lower, down closer to 50-something meters. So the 25-meter Cretaceous ice sheets of this size would be close to half the size of the present Antarctic ice sheet. So they really would be a very major ice volume indeed. Let me say at the outset, I'm a complete skeptic of this. I think this is wrong. I think there's an alternative explanation. I think this was an ice-free period, or largely ice-free period, and the whole premise of my work on this is antithetic, is the opposite of this assumption. Partly, just to give you a little bit of a snapshot of the CO2 story for the Phanerozoic and the Cenozoic. So these are IPCC graphs. The upper panel shows these array of reconstructions, attempted reconstructions for CO2, atmospheric CO2, spanning the last 400, 500 million years. And we may be talking about CO2 levels during the Cretaceous, thousands of ppm. There's an enormous amount of scatter in the data. This just shows the CO2 proxy data for the Cenozoic, which is more recent. And there is an enormous scatter for sure, you know, possibly low, but possibly extremely high. And if anything, the Cretaceous may have even been higher than this in CO2 level. But we may be talking about, you know, a couple thousand ppm, I think, for argument's sake. So the idea that, you know, it's a very important question. Could such Antarctic ice sheets be sustained with high CO2 levels? I think it's one obviously very important question. And I'm actually not going to summarize all the oxygen 18 data, which is actually this review article tried to summarize the oxygen 18 evidence for or against these kinds of glaciers, because O18, as you know, can be a proxy for ice volume. And there are studies during this period that show no variability in O18 during that time. There are others that show small variability, which some workers are interpreting as the potential of small ice sheets. I'm not going to try to summarize that, and I'm not going to try to prove to you this is wrong. I just, my point in these opening slides is just to make the case that it's a very equivocal. The jury is completely out on this question. It could go one way or it could go the other, in my opinion. And I'm no expert on, you know, the paleo-botany of Antarctica at that time, but there's abundant biologic, you know, fossil evidence for extreme polar warmth during these time periods. Very equable, I still have trouble saying that word, equable climates with much higher polar temperatures. But, you know, the little I started to compare that this model against some of the fossil data. For example, there's good reconstructions for paleo-botany on the Antarctic Peninsula, and you see reconstructions like this for, say, close to 90 million years ago. The climate was generally warm and humid to allow growth of large conifers with mosses and ferns. Mean annual temperatures close to 20 degrees Celsius, that's 70 degrees south. You know, and when I compare, I didn't bring the maps, but when I compare the Conto model, this model with that kind of temperature, it looks to me like their model is much too cold for that kind of paleobiology at that location. But again, the point is not to prove it one way or another. I think this like I say, there's a strong possibility that there will not be evidence, and eventually it could be proved that there weren't any glaciers of this size during this time. I am going to be referring to the sea level records. My work has largely focused on the what's called the sequence stratigraphic record. This is the oil industry data sets that were pioneered in the 70s by Exxon. These are, and this is I find this the most powerful data set for the kind of case I'm going to try to make to you today, because it's they literally are trying to show the sort of two-dimensional sedimentary surfaces as they evolve over time. So these are done by seismic profiling and decades of you know, skill in terms of interpreting these seismic profiles. But there is sort of these generic, what I'll call transgressions and regressions that have long been observed worldwide on continental margins, and apparently over the entire Phanerozoic. These just show, this is a recent paper from geology from Neil and Brew, where they just show the sort of generic rock cycles, sedimentary rock cycles, where you get these kind of retrogradational, I love the language of sequence tree, retrogradational coastal onlap, prograding surfaces, and then they get these very abrupt sort of erosive cycles where there seems to be an abrupt shift of deposition basinward, which creates sort of a very sharp seismic horizon, which is called the sequence boundary. I don't need to be too wrapped up in the terminology here. I just try to give you some of the generalities. But these are sort of the generic sort of landward and basinward cycles in sort of sedimentary deposition. And by all accounts, these existed during the Cretaceous as well. So one of the very long-standing questions is what causes these cycles? So I'm going to propose an alternative framework to the fact that maybe ice causes a cycle. My framework is ice-free. And my framework is that there was no or insufficient or non-existent Cretaceous Antarctic glaciation to explain those coastal transgressive regressive cycles that I just sort of generically showed you in the last slide. I also don't believe we're going to find a similar eustatic mechanism. Eustatic, I use that term a lot. That's used to see. It's the sort of the geologist's preferred term for global sea level change, or what you could refer to as the vertical movement of sea level. So the second part of my framework is I don't think we're going to find another eustatic mechanism that's equivalent to ice. with sufficient amplitudes or frequencies that could explain these persistent transgressive regressive cycles. So with those two bullets, I think it means something very important. I think it means that eustatic sea level did not rise or fall so rapidly. I mean, if you can't find a mechanism to cause it to change, then that means it didn't change at the amplitudes. Yes, Elaine?
Can I just make sure I understand eustatic? Does that refer to rebounding, like terrestrial rebound? No.
No, this is
the average, global average sea level.
Okay, good, thanks.
Yeah, I timed this talk to be about 45 minutes, but if you want to interrupt, I think it might be.
Well, that was just.
I'd be happy. I think it might help. Anyway, so the third bullet in my framework is this, and then I think there's only, if this is true, if this eustatic sea level did not change, and you observe these large transgressive sedimentary cycles, I think there's only one alternative: that the sedimentary systems themselves are cycling, with perhaps very weak or no eustatic forcing. And then the final goal, which is a very important part of my talk, is that I believe there's a complete set of parallels between this situation I'm describing here and the 100,000-year late Pleistocene ice volume cycle, as I'll try to explain to you. And indeed, if you line these two cycles up against each other, so on the left I have the ice house world, and on the right I have the greenhouse world. Over the years that I've been working on this, I just feel there's just a systematic set of parallels between these two problems that I don't believe is accidental. At the top, I've sort of shown like what I call the target cycle data, and on the left, of course, is the famous 100,000-year 018 record for the late Pleistocene, showing the very prominent 100,000-year cycle. That cycle, well known to all of us, one of the greatest mysteries in paleoclimate for sure. Equally important about that cycle is this iconic asymmetry that Wally Broecker first coined as being terminations back in the 70s. To my knowledge, I'm welcoming your opinion on this. I still don't think the asymmetry has been explained as what its significance is yet, but it's certainly a key feature in the ice volume cycle for the 100,000-year cycle. And on the right, the early renditions, I'm showing you here some of the 1987 release from Exxon for their Cretaceous cycles, which again emphasize a very prominent asymmetry. And the asymmetry was caused by that abrupt offlap that I described, where you create this erosion, this sort of sequence boundary. And the early charts emphasize that it's asymmetry, which in the early days when I was working on this really struck me as something quite interesting. The idea that these two cycles that we're dealing with have some kind of unexplained asymmetry to them. If you move down to what is the actual system we're talking about in each case, there is a mass, what I will argue is a sedimentary mass in each case. So this is a cross-sectional profile of a generic Laurentide ice sheet for the late Pleistocene. And there is, of course, a mass that's moving horizontally. It's subject to lateral mass transports and substance. And there's what I call a stratal surface that exists for sure in this case, which is interacting with a snowline. I'm going to make a big deal about this configuration here. If you move over to the sea level side of the story, once again, there's a sort of a mass transport, not of glacial mass, but of sedimentary, true sedimentary mass. Subject to lateral mass transport, you get an evolving 2- and 3-dimensional stratal surface, evolving through time, and again interacting with an equilibrium line, which I'm going to call sea level over here. If you sort of move down to how these things are modeled, and these details are in, I have supporting papers that I'm going to provide online, you'll see that these are nonlinear diffusion models in each case, and in fact they're actually retarded transport models if you work out the mathematics of this. You get actually another key feature is you get a sort of a depositional front in each case, which is very nonlinear kind of transport system. My talk, though, is going to focus around these last 4 bullets, which I believe are parallels between the two cycles. Milankovitch theory showed that the snowline forcing was insufficient to cause this cycle. So I'm going to hopefully make that point very clear. I'll also trace out to you what happened from that finding. In fact, what happened was ice sheet models then developed, nonlinear ice sheet models developed over the 80s and 90s when this work was in its heyday, that actually were able to explain the full cycle. And in fact, we're able to almost auto-oscillate, and I'll try to give you a flavor for that. On the right-hand side, I've been arguing that I believe Cretaceous climate theory may be showing an analogous thing, that this equilibrium line that's so important to these sedimentary systems may not have been fluctuating greatly. And my feeling is, why couldn't traditional sedimentary systems oscillate the same way climate modelers have shown ice sheet systems to oscillate?
Can we back up 1 minute?
Sure.
The thing with the sequence stratigraphy, when they talk about these eustatic changes, like these first order, I mean, they have several orders.
They have several orders, yeah.
The major ones would be considered eustatic, which would be of global extent. Now, I'm not quite clear, what is the mechanism you're proposing, for the sedimentary sequences to auto-oscillate? I can understand, like, let's say deposition, you're having major inputs from rivers, which might be modulated by climate change, perhaps. But that would be more of a regional nature. I don't see that as being global.
Well, we can get a discussion to the extent these are global or not. I don't require that they're global, but I think the framework I'm proposing could explain some of the synchrony. But the mechanism, I'd like to actually show you one mechanism at the end of my talk.
Okay.
Again. Part of what I've been struggling with when I'm working with is what do we consider a sedimentary system? If you type in sedimentary system for an internet search, you'll come up with a lot of those sequence stratigraphy terms I showed you. But there's another part of sedimentary systems, another way to look at sedimentary systems I think is much more general, and it's embodied by this quote. It's a very old quote from Joseph Burrell. Let me please read these because they're important to my case. The sediments whose interpretation form the base of Earth history have been characteristically deposited with respect to a nearly horizontal controlling surface. This surface of control is base level. Sedimentation as well as erosion is controlled by base level. It is the surface at which neither erosion nor sedimentation takes place. Base level may be used as a wide and inclusive term, applying both to land and sea. And the reason I'm writing this latest paper is because I've decided that maybe this simple configuration should maybe be the basis for what constitutes a sedimentary system. Let's just, taking Burrell's, I've drawn here an equilibrium line and a sedimentary surface as two intersecting surfaces. This is a very ubiquitous configuration. It exists with glacial systems, it exists with coastal sedimentary systems. It even exists in the deep sea with a calcite sedimentary system. There is a horizon there, once again, the Lysocline calcite compensation depth, where there is, separate zones of accumulation from non-deposition. Very, very general, and I'm sure when Burrell formulated this, he must have been thinking, I don't think he mentioned glacial systems, but I fully feel these very, very different, very interdisciplinary systems fall into this category of having this kind of simple geometric configuration. And if you just start with this, it's elementary school almost, you can define a very basic problem that applies to any of these sedimentary systems. And that is, all relative dimensions on this surface are going to depend equally on the movements of the two surfaces. So if you look at a few key relative dimensions, so for example, this x-intersect, I'll call it, and I put this in a Cartesian coordinate system, so I have a formula for the straight line, and I have the elevation for the equilibrium line, so you give those nice simple formulas, and you work out what the intersection point depends on, and you see, of course, it depends on both surfaces, the equilibrium line and the elevation of the sedimentary surface. I apologize for spelling out something that may seem almost like high school arithmetic, but I've been trying to publish these in some of the more descriptive geology journals, and I have found you have to be very, very explicit about any of the equations, so that's why I went through this in terms of this talk, spelling these out. I'm not trying to knock the geologic literature, but I find that any mathematical equations like this have to be spelled out very carefully. Another, sorry. Let me see. Okay, another relative dimension would be, say, water depth. And there again, if you work out the formula for it, you can see equally well that it depends, as it has to, on the two surfaces. These are relative dimensions. Now, these relative dimensions can be important proxies, in models or our conceptualization. This could be, for example, the separation from an accumulation zone to an ablation zone, or it could be the separation from a subaerial environment to a submarine environment on a coastal system. So they could be proxies for major processes on the actual sedimentary systems. And so I'm going to propose a framework now, following from this simple configuration, and it's really no more complicated than this simple equation. We all learn in grammar school that if you have one observable, 5, and it depends on 2 unknowns, you can't attribute you can't say what combination of A and B led to 5, obviously. And that's because there are an infinite number of combinations that can lead to that result. So we all learn in grammar school that you have to have a second independent equation involving A or B to observe, to sort of make the attribution or separate the contributions of the two unknowns to the observed result. So going back to this framework, I'm just going to take that grammar school topology, and I'm really writing this paper about this classification I'm going to give you right now, because it's very simple, and I think it's very general, and I think I can apply it to very different systems. So I think it's important to sort of get it out there in the literature. But let's call approaches where you somehow reconstruct the equilibrium line independently. I'm calling those A-type models in my framework. And let's call the opposite choice where you reconstruct the sedimentary surface somehow through time changes. I'm going to call those B-type models. And really, this is going to map my talk out for you. I put the Pleistocene ice house problem down here, the Cretaceous greenhouse problem up here. I first, again, want to show you that Milankovitch theory and subsequent ice sheet models were an A-type theory. I then want to show you that it's harder for me to summarize this. B-type theory would be reconstructions of the glacial surface through time, and to the extent that has been done, we can chat about. The target data, the observable, I'll call it, that depends on so intimately on these two unknowns, is going to be the 018 ice volume record that I just showed you. On the Cretaceous side, this may be a little technical, abstruse for those of you who aren't familiar with backstripping, but I want to show you that backstripping models, sediment core analyses, are actually a B-type model. This was the second thing that prompted me to write this paper, something that occurred to me a few months ago. I will describe what A-type models are for the Cretaceous sea level problem. And then the target date is going to be that the coastal onlap exon curve that I gave you in the beginning. So on to Milankovitch. Okay, this is fun to actually you don't have to show that Milankovitch in the A-type model isn't hard to do. All you have to do is get a copy of the canon of insulation, which we have here, and I have it here for you to look at. And I hadn't read it, carefully until I guess recently. But if you read the preface to it, Milankovitch goes through a very lengthy, intimate discussion of his thinking on the orbital problem, and major breakthroughs he had at each stage. And at the very end of the preface, you come to this remarkable passage that I think needs to be disseminated more when we talk about Milankovitch. And again, I'm going to read you in detail the most important result. This is Milankovitch. The most important result concerned the question of whether the influence of the astronomical elements on the march of insolation was sufficient to fully explain the largest climatic fluctuations of the Quaternary. I began by analyzing mathematically the connections between the altitude of the snowline and the radiant energy corresponding to the caloric summer half-year. I found that a shift of the snowline by 1 meter corresponded to a change of this energy by 1 canonic unit. With this result, the most important climatic effect of the prehistoric course of terrestrialization, the displacement of the snow line caused by it, could be determined. So, what did Milankovitch do? It's really pretty simple. He was working, of course, with insolation as a function of latitude on the surface of the Earth. And moreover, he worked with, he was able to, through his orbital calculations, calculate what he calls the half-year caloric summer at each latitude. He was able to calculate that half-year caloric summer radiation going back in time. We all know that if you have any familiarity, you know he was able to do that going back in time. So then what he did was he took the modern day caloric half-year summer insolation at each latitude and he correlated with present day mountain snowline elevation from Köppen. And by doing that correlation, he came up with this 1 meter that he describes here. So it was a straightforward present day regression between existing insolation as a function of latitude and snowline elevation as a function of latitude. Then what he did is he then took that correlation coefficient and he applied it to his historical tables at key latitudes like 65 degrees north and so forth. And you should further read it because it's remarkable. He found that they weren't that dramatic, the snowline elevation changes he calculated. He found they were on the order of a half a kilometer to about a kilometer. And I can't help but, reading it, help but think he must have been disappointed because, half a kilometer, it probably didn't seem like enough to explain, 1,000-kilometer ice sheet waxing and waning during the ice ages. So, and indeed, he said he even he even says this can't be the cause by itself, the snow line. So it must have been a disappointing result, I can't help but feel. And he actually went on to think, well, there must be other feedbacks that are kicking in, that are creating the major changes that we're seeing in the ice volume. And indeed went on to consider albedo. But my point is made here. This is an A-type model. He is mechanistically, whether you accept it or not, is not the point. I mean, but the point is to categorize it as to what the strategy was here. He is mechanistically reconstructing the snowline elevation changes through time. And that, to me, that's the epitome of an A-type model. So what would be a B-type model for the, I want to show you what happened as a result. Then with this result, that the snowline was constrained to rather small, half a kilometer, modelers started working on this problem. Given that constraint on the snowline, could we simulate big ice sheet volume changes? And indeed, they were able to eventually, and there are many workers who worked on this, Gill, Birchfield Hyde, Pollard, others. This shows results from Pollard that just as one example where he was able to get very large amplitude ice volume changes with small Milankovitch style snowline forcing changes. And you have to look closely, but you'll see he applied sort of Milankovitch scale, half kilometer oscillations to the snowline, but was still able to get very enormous ice volume changes because of feedbacks. And what was happening was on that top right panel, as the ice sheet expanded, you get this enormous geometric expansion of the accumulation zone of snow on the ice sheet, which is a positive feedback. And this was enough to actually kick in sort of unstable growth on the ice sheet. Then it reached a certain maximum size and some stabilizing forces kicked in, and you see the ice sheet sort of retreat back. And indeed was able to actually get plausible simulations for the 100,000 year ice volume cycle. So now, one reviewer of a paper when I tried to submit it said, well, is this an A-type model or a B-type model? Because he's simulating snowline elevation changes. Well, I maintain this is definitely an A-type model because the constraint was on the snowline, and working from that constraint, they were able to then deduce what the remaining ice sheet volume had to be to match the 018 record. In other words, the glacial surface reconstruction is dependent on that independent construction of the snowline. To me, that's an A-type model. We can discuss this if you see it another way. Another way to put this is, without that constraint, Pollard could have probably varied the snowline any way he wanted, and probably could have come up with multiple ways to simulate this, but with really no constraint on, say, the snowline. So I maintain this is an A-type model. Well, what would B-type models be to me then for the Milankovitch ice sheet problem? These would be, in my classification, these would be attempts to reconstruct, however you could do it, the glacial surface through time from field data. And I can't really summarize it to the extent that's been done. I mean, of course, we have many constraints on how big the ice sheets got at glacial maximum. I believe there's probably snowline data from mountain evidence as to how tall they got at certain stages. Isostatic rebound data gives a sense of their mass and size. But to me, again, this would be an attempt to get a time series for those reconstructions. I don't know the extent to which it's done. It probably would have been a hard approach, but in my framework, that would be a clear example of the B-type approach. So now I want to jump back to the Cretaceous problem and take the same AB formalism with you and apply it there. So here, I'm going to redraw now the sedimentary surface. This configuration I've described, and I've also put in here a sediment core, which is in black. And I want to link up with sediment core analysis models. And what they do in those models is they treat substances positive downwards. There's a basement that's subsiding. We can talk about what's causing that here. It's thermal subsidence. But it's in those models, in order to make a link between this picture and those models, I have to put my coordinate system here is all I'm saying, and measure BD, basement depth, downward. So the terminology is BD refers to the basement depth, the bottom of the sediment core where it reaches, say, basement. Then there's a sediment core which has a thickness I'll call S star. And then here's my old water depth that I showed you at the very beginning, which is that critical relative dimension. And then I'm placing sea level against this coordinate here. I'm measuring it positively from this coordinate, so I've labeled it, SL. So these are all 4 positive dimensions. BD is positive downwards. S star is sediment thickness is positive. Water depth is positive, and sea level is positive. And I think you'll accept that if you want to work out the equation that relates to 4, it's that one on the upper right. The water depth is simply the difference between the sea level elevation and the sediment core top elevation. The sediment core top elevation is given by the difference between S star and BD. S star minus BD gives you the sediment core top. So this is a very straightforward. It's completely analogous to my first formula when I did this with you with the Cartesian coordinate system. So now I want to ask a simple question. If you're going to use an equation, if you're going to use this equation to determine sea level, what kind of model is that? Well, if you're going to determine sea level from this equation, you're going to have to know the other 3 variables. I think we can all agree on that. You're going to have to determine WD, S star, and BD. And we can. I'm not going to spend time here telling you how they extract this from the cores. We can talk about that. But clearly, if you're going to get sea level from an equation like this, you're going to have to get WD, S star, and BD first, and then you can deduce sea level as the residual. But if you deduce S star and BD in my framework, you've worked out the sedimentary core top height through time. This is a B-type model. Is my point here. So I just want to briefly show, because I'm assuming none of you are familiar with the backstripping equation. No. Okay, that's a fair assumption. Yeah, well, this is the major equation used by Miller and others to actually deduce sea level, hopefully. But I just want to show you, and this equation, I won't knock it. I won't knock it. Not that there's anything wrong with it, but the way it's described in the literature is incredibly convoluted. What I really just want to make the point to you today is this equation is completely consistent with my equation I just showed you. In fact, if you look at it, it looks different at first, because there's a WD over here, there's a sea level term, there's a sediment column term with some density terms, and then they have this thing called TS. Well, what's that? Well, when they analyze, they don't actually reference the core to the actual basement depth, because they don't know what that is through time. What they reference it through is something called the tectonic subsidence depth, TS. And that's actually the depth of the basement would occur if you unloaded the sediment for this. And I'm not going to spend a lot of time trying to reverse engineer why they did this. This has to do with the early days of sedimentary basin theory, where they were trying to understand what was the driving force behind the formation of basins, and it was realized it had to be thermal substance through time. So there was a lot of focus on this so-called thermal substance, TS. And also they do this because they believe they can model that in the analysis of this equation. But BD and TS have to be related. This is just the depth that would happen if you unload the sediment. Well, that's not a hard thing to relate. If you take a little isostasine model, you have a sediment load and you point load it. I'll just leave this as an exercise for students who want to try to do this. But if you just take a simple airy point load isostasy, you'll actually come up with this equation I have down here, that the basement depth is actually equal to the tectonic subsidence depth plus some density in terms of SR. That's not the point. If you take this equation and you put it into either TS or BD, you'll get the other equation. Is really all I'm trying to show you. That mathematically, this enigmatic backstripping equation is the same as this simpler intuitive equation I've been describing to you. And to me, that means something. That means that these backstripping models that have been, that they've been wrestling with for all these years are actually equivalent to a B-type model. Give me their data, and I can then, from their data, I can work out S star and BD, and therefore I can, in principle, try to reconstruct the sedimentary surface elevation changes through time. So this is a B-type model. This may seem like a little gibberish to you, but this was very important for me to see this, because it fell into a framework between the two disciplines that I didn't see prior to this. So that's a B-type model. Now, what are A-type models in sea level theory? Well, these are easy to describe. These would be direct reconstruction of the equilibrium surface through time. Now, how do we do that? Well, we can do that actually through mechanistic models. My PhD thesis was actually dealing with the ocean volume changes, where we can actually calculate changes in ocean volume due to tectonic spreading rates in the ocean floor. And so it's really the bathtub model for the ocean. You can change the level of the water through changing the walls of the bathtub, the floor of the bathtub, or you could change it by removing water, say in the form of ice. So these A-type models would be those kinds of reconstructions where you mechanistically are reconstructing what sea level did through time from these mechanistic causes. Which brings me back to my opening point. If we don't find ice sheets during the Cretaceous, and we don't think there's another mechanism that's equivalent to it, that's not non-knowledge to me. That's a definite finding. That's an A-type reconstruction. You are therefore showing that the sea level did not change that dramatically as you would think it would need to for ice sheets. It was a relatively quiescent sea level. So that's an A-type reconstruction. The absence of ice sheets is an A-type reconstruction. So, which leads me to the final section, which is I wanted to say, well, if we can conclude that sea level didn't vary much from the absence of ice sheets, and we observe these large sedimentary transgressions and regressions that I sort of just gave you quick snapshots of, what does that mean? Well, it means to me there's only one alternative. Somehow the sedimentary system itself is undergoing large variations through whatever cause we can discuss. Now, I believe it's going to involve seeing or modeling a nonlinear feedback within the sedimentary basin systems themselves, which I want to just kind of walk you through real quickly in my last few minutes here. And sedimentary systems are complex. There's no question. I'm not, and in this last few frames, I don't want to argue that I've captured all the complexity of coastal sedimentary systems. But I do want to take refuge behind it. This was a recent essay by Chris Paolo where he argued that in modeling, simplicity isn't simple, and that it's not necessarily a good thing to try to capture all the fluvial complexity of coastal systems, but maybe it's better to try to isolate certain features that we think are important. And really, if you look back on those pictures I showed you of even Milankovitch's theory for the snowline and Pollard's model for those are low orders, those are simple models. They are not capturing all the complexity in the real world for sure. But nevertheless, they were extremely important simple models. So in that spirit, I would like to argue that we should be embarking on similar kinds of investigation for how a sedimentary system, a passive blob, like they modeled the glacial system, how could that auto-oscillate? Because they were able to actually show that, Michael Gill, for example, that it could auto-oscillate. And I see nothing wrong with asking that question. Why couldn't sedimentary, and for some reason I'm the only one asking it as far as I know. So I want to give you one example of one flavor for what could be causing an internal oscillation. And I think there is a reason this hasn't happened as quickly here in this field as it did in the ice sheet field. I think in the ice sheet field, the feedbacks they were dealing with were a little easier to understand. Albedo, take albedo feedback. You can explain that to a kid. The glaciers grow, more albedo, sunlight cools. Children understand that. That feedback that I showed you with the Pollard model expanding, that took some pretty brilliant people actually to think of that. It was Wiertmann and co-workers in the 70s. They sort of realized, hey, there's this geometric expansion. That's that was harder, but still, I think, you can sort of visualize it. I think that the nonlinears that are happening here are not as visible, and they're certainly not things like albedo. But there's I think there's one very fun nonlinear staring at in the face of this picture, and that is if you're going to model this as a diffusion model, which is how you would normally model a simple model for sedimentary transport. You would take a surface slope at any location and say the mass is proportional to that surface slope, and then you need a diffusion coefficient in front of that slope. And that gives you a diffusion model. But to simulate something like this, you would need a nonlinear diffusion coefficient. I believe it's mathematically true that you could never get some kind of abrupt equilibrium change in a diffusion model without some kind of nonlinear diffusion coefficient. And indeed, I think you could argue this is sort of a retarded diffusion. As the sediments move basinward, they encounter less vigorous fluvial weathering transport processes. I think you could plausibly argue that the diffusion coefficient here would probably be weaker than it is over here. And just taking that simple example, here's just a graph of what might be such a diffusion transport coefficient. And all I'm showing here is, imagine yourself on a certain point on the sedimentary surface, and imagine sea levels very far basinward, like this. I have the diffusion coefficient high because that means you're exposed to the aerial environment. And let's imagine now sea levels coming in and eventually floods you and moves landward. I have the diffusion coefficient going here because you're inundated, at that point. So this is just a generic example of and there are simple formulas, a hyperbolic tangent for this. And what I did in this last exercise is I just basically did a low-order nonlinear diffusion model for what might be a coastal sedimentary system. So I'm not going to spell the details in great detail. They're in my climatic change paper, which I'll make available online. But basically, this is in the spirit of Chris Paola, simple low-order modeling where I have two volumes, a landward model and a basinward volume, and I have them connected by a slope-dependent surface slope here with this kappa that I just showed you is nonlinear. I kept everything fixed in this, by the way, upstream fluxes of sediment. Sea level was kept fixed in this model. Those were parameters of the model, but I held them strictly fixed. And this was totally non-dimensional. My goal here was not to explore the phase space of these parameters. There's so much data and information that we don't have that's not easily accessible. A lot of that Cretaceous data is proprietary. It's, to get some of the geometries and so forth. But anyway, I think you can follow the drift of what I'm doing here. So I just did it's a 3-equation model, just mass conservation with this nonlinear diffusion coefficient. And I didn't tweak this at all, but happily for me, it just started oscillating. And really, what's happening conceptually is as the surface is getting exposed, there's a more vigorous transport of sediment into the basin, which kind of progrades the surface out, and then it eventually stabilizes and retreats in the other direction. But these are just completely unforced changes in the relative sea level for this model, by the way. The relative sea level is just the x-coordinate of the intersection point, moving back and forth here. So this is just an illustration of something that could go auto-oscillatory. One last point before I finish, because I'm really almost done, Vivian. One other thing that I think is, again, there's a slight asymmetry here, which it shows you not necessarily that this is the cause of it, but I do believe these nonlinear systems can show asymmetric cycles, which was one of my earlier points. If this asymmetry is indeed a part of these cycles, it shows you that these kind of models possibly could explain some of that asymmetry. I have my last slide here. Should I just do that and then take your question, Vivian? So anyway, I'm starting to breeze through that. I recognize that some of this may be specialist jargon in some of these slides, but I at least want to give you just an overview of this. But I do think, I hope you got a sense for the title of my talk that I believe these two different systems, Milankovitch ice sheets modeling and paleo sea level studies, have been confronting the same sedimentary problem. And that sedimentary problem is no more difficult than that diagram I showed you, that you have these two surfaces interacting. You've got to work out the history of one of the surfaces in order to explain the cycle. And I hope I showed you that these major efforts to do this have been tackling different parts of that A-B framework. I can't make it simpler than that. And I don't think the parallels stop there. I do think there's this sequence of analogies. My final comment, I promise, is that if it indeed turns out, if it turns out that we end up simulating nonlinear auto-oscillatory sediment, I think that's going to be very important. Because that Pollard model I showed you, that's not accepted as the explanation for the ice ages. It's just one candidate hypothesis among many, involving CO2 and so many other things. But I think if we see some kind of similar dynamical system going on, I think it ups the ante on that there's something going on with those sedimentary systems that may be part of this, both those stories. And I think will be very important for many reasons. So with that, Lane, when you want to put on the lights, please? And
oh, yes.
Thank you. I don't want to.
Yes.
I think some people are trying to see. Yeah.
I'm just still a little puzzled on some of the mechanisms that would cause this oscillatory behavior if you want to rule out eustatic changes in sea level. You mentioned this thermal subsidence, but that is
Smooth.
something that smooth curve over time, gradually diminishing over time, I would think, right?
Right.
Anyway, and then so you have two things that could be at work. Either you're going to bring in more sediments are flowing down the rivers, whatever, and depositing offshore, or there are changes in sea level, or some combination of the two.
Fine. But if we rule out that the changes in sea level were weak because there were no glaciers, that's my whole. If you accept that,
then it's coming from the sediments.
There's got to be some kind of sedimentary dynamic.
All right. Well, that still begs the question of why you get worldwide changes.
Well, okay, fine. Why not? If it's an internal instability like this, a local instability of the kind I illustrated here,
Yeah.
Why could that not, if it's local instability, it could operate anywhere, you know, this sort of nonlinearity is
But
operating.
relatively synchronously? I mean, at least synchronous in a geological sense?
And here, I love this question because I come back to the 100,000 year cycle. There's a lot of synchrony in that too, between the ice sheets. You know, the Fennoscandian Laurentide, you know, there was synchrony there too. And I don't believe
But that's global climate change that happened.
I don't believe the synchrony is beyond the capability of these I think these nonlinear systems could synchronize, and you know that's a whole other discussion. But I don't see it. It's not. I don't think there's anything ruled out on my mechanism here. I mean, I'm not sure I understand your criticism. I mean, you're saying to me because these are synchronous, which some people don't accept, but I think it's fine if they are.
Mm-hmm.
That somehow you can't have
a localized mechanism can propagate on a global scale.
Well, through climate effects. And I fully believe these sea level oscillations could have effects on things that we don't know enough about yet. Small scale CO2 oscillations during these times.
I thought you ruled out sea level.
CO2.
Oh, CO2.
CO2. The question of synchrony is extremely important. I agree with you. I don't think my model that I illustrated here is going to be ruled out by synchrony. I think it's possible that this kind of model could be synchronous in many locations. Again, I keep coming back, you know, the fact that it could be a local instability is fascinating to me because it also would imply to me that it should just continually operate, which is another characteristic of this sedimentary sequence cycle. It seems to be operative throughout the Phanerozoic.
Mm-hmm.
But you know, I guess my short answer to your synchrony question is I believe this kind of mechanism is probably going to require coupling through other climatic things to maybe get these different systems in synchrony. But I don't know the extent to which the synchrony has been established. You know, some workers say they are synchronous, others don't. I tend to believe they are, but I don't believe it is dramatic vertical sea level changes of ice sheet sizes.
Stuart, in your simple model that showed the oscillation there, was the deposition rate constant over that whole period?
The inflow of sediment is constant. This is held fixed. It moves in. There's substance going on here where the sediments are getting buried. So in the model, there's I remove sediments through substance.
Okay, but if you advance one slide, I think, and you see that oscillatory pattern, it seems to me, Vivian, what you're saying is that maybe there's a global synchronization in terms of the inputs in sediment, you know, a hydrologic cycle effect globally. And I wonder if there could be a feedback between the dynamics that you're talking about in terms of this, with that input.
Well, look, yeah, you could create this cycle just by varying U.
But it sounds like a feedback is really pushing.
And yeah, you want to vary U, fine. Explain to me why you're varying it, and try to defend that model. Okay. I'm generating a cycle, and I'm showing you where it's coming from inside the system itself. It's coming from this nonlinear, in this particular case, this nonlinear transport term.
Yeah.
You know, medial each side instability. And then we can argue about, you know, who has the stronger case. You know, explain to me why this U is varying. And then here I have an internal mechanism that I can say is causing the oscillation.
I don't necessarily think I'm raising a conflict there. I think what I'm saying is that the local effect becoming synchronized globally could have an interaction in the U term there.
What is that thing when we have a clock of different oscillators
Yeah, you know, again, I guess I haven't spent much time thinking about the synchrony because you know, until it's established, and unequivocally, and again, I'm not worried about it. I just actually think, well, eventually, I think a set of models like this could address the synchrony. And I think it's going to involve some climatic teleconnections, and the most likely would be some kind of greenhouse gas. You know, these are the continental margins. They probably have a strong role to play in, you know, the biogeochemical cycles over time when you get these transgressive, regressive cycles, and no doubt strong perturbations to the carbon cycles. But we just don't know what happened to CO2 on those small fluctuations. Yeah, I showed you the CO2 data. We barely know the order of magnitude of the Cretaceous time. So I think ultimately my feeling is, and again, this is just opinion, I think the synchrony in my case is going to require some kind of greenhouse gas climate, you know, forcing feedback, you know, that's going to synchronize these sediments or these sedimentary systems.
Do you wonder if this simple model gives you this particular oscillatory feature, but if you built a more complex model, the feature would completely change, just in the same way, like, you know, GCMs don't find this hysteresis in, you know, freshwater input, but all the intermediate complexity models do.
Oh, for sure. I mean, good God. I mean, this would be too lucky if I, yeah, I rig up some little 3 OD equation and it has, you know, I'm the first. Again, it was meant to be illustrative. Is it robust? I guess you're asking me, is it robust with a? I have no idea yet. You know, it's hard to build these kind of. I consider it hard to build these nonlinear diffusion models, and maybe software is getting. You know, I guess I'm an old timer. I like low order models. I didn't want to spend tremendous amounts of time on something, you know, that's still a little speculative in terms of its origin. But the answer to your question is no. I have no guarantee that this will hold up. And I think it's an interesting thing I'd like to see checked out, but I don't have a guarantee that it'll hold up. I mean, I'm seeing it in a low order example like this, and so the answer is yeah, I don't know yet.
There's a lot that I don't. Yeah, I mean, this is complicated with me. But before anybody decides to try to invoke changes in wetlands and methane emissions on the coasts, because that's what everybody loves to do, I just like to say that wetlands that are on coastal margins with salt water produce practically no methane whatsoever. Just want to say that now before anybody's doing, because you know you're talking about biogeochemical cycles and
these are very, by the way, these are very long time scale. I don't think I mentioned this. These are like somewhere between 1 and 3 million years. These sedimentary cycles that I'm talking about for the Cretaceous. So they're multi-million year cycles, which a lot can happen in a few million years for exposure and your point is well taken.
Except that it's saline water, which is what all the coastal wetlands are. Then methane. You're not allowed to use methane. just commenting only because
I know.
This is what everybody. I mean, this is so common. It's in millions of years. It's in thousands of years. It's in whatever. Everybody loves to decide that we don't know anything about wetlands, and it must have been wetlands. And there's a couple of really basic things that we do know about wetlands, which eliminate some suggestions, kind of. Right
Well,
in the beginning. That's all. I'm just.
When
I'm
you
sort of,
go on these
I'm half
timescales,
kidding and half serious.
when you go on these timescales, I wonder whether we should be reinvoking some of the old ideas like Wally Broker, where which didn't hold up for the Cretaceous time. One of his earliest hypotheses I remember was as you got, say, the ice sheets grew, and you got continental exposure, you get phosphorus and loading nutrients into the oceans, which would then stimulate biological productivity, draw down CO2, right? My memory of that is the timescales were insufficient. 100,000 to really cause that kind of perturbation. I don't know if that's still true. Maybe Wally on this longer timescale, maybe that is a mechanism that would operate here a couple million years. All right, thanks for sitting through that complicated story. Again, I'm trying to get it as simple as I can. I think I see it, but I have been having trouble getting this published, even though I think this is the strongest case I have had to link these two problems. I don't quite know what is the conceptual barrier to stuff. Frankly, it was just rejected from American Journal of Science. They had trouble finding reviewers for this. So it was like, because I guess one guy wrote, I work on his A-type models. I know nothing about B-type models, and it was like, it's a little frustrating doing this interdisciplinary work. The journals aren't always ready to handle it as much as they like to say they will.
Sorry, you earlier mentioned how it's really hard to do B-type models for glaciers. And I wonder, now you're taking that problem underwater, to a lot of continental shelves. Is that an easier problem? Because of the geologic surveys that have been done by ExxonMobil and others, or?
Well, I think these B-type models are very hard.
Yeah.
And in fact, the reason I did all this on this backstripping patient, spent all that time on it, was because I wanted to show it was a B-type model for my framework. But I also wanted to show, try to conceptualize how difficult that is, what they're trying to do.
Yeah.
They're trying to calculate the top of the sedimentary column 90 million years ago of a system that's subject to subsidence, variable sediment influx rates. Imagine the challenges. You know what they have to do that, by the way? I didn't give you a sense of how complicated it is. From the sedimentary core data, they have to extract water depth from the paleo-bathymetry of the critters in the column. They have to decompact the column through porosity curves. Then finally, they don't even know how it's subsiding, so they have to model the tectonic substance as an ideal, and then think about all that, the potential error in that. and how difficult that is. This was really one of my motivations for trying to show was B. Because that's an extremely difficult thing to try to reconstruct a sedimentary surface elevation 90 million years ago. So I'll leave it there. Okay, so the paper will be online. Any of you have any questions or recommendations as to how I can make this easier for Lehigh? It's a geology department. They may know a little more about backstripping. I don't know. But thank you so much for sitting through this. It really helps me.